All right, let's continue in 5.2, diagonalization of a matrix. So here's the theorem that we started, and I went ahead and did, actually I guess I did all the proof, but it's easier to talk about sometimes because especially this notation. So let's go ahead and let A, D, and C and lambda be defined above. So normally you might rewrite everything, but not always. You know, you can kind of just say it's from the statement above in the theorem. All right, so then we have what C is, right? So you write C times D. So you're saying if this, all of this up here is assumed, then you have this equivalence, meaning it's an if and only if. So it implies if A times C is C times D, that's saying that these lambdas and these are eigenvalues, etc. And then it goes the other direction. So you really want to work with this. You want to write down, we're going to write down C times D. It doesn't matter the order really. So C times D is here. So C are those vectors, right? And then D is the diagonal matrix. So here's your diagonal matrix. When you do this product, these are columns times the diagonal matrix, you end up getting each diagonal times each of those vectors. So you get this form, and those become those column vectors with the lambdas there. And if that's not clear, do like a little 2 by 2 off to the side and check that. So then we can state what AC is. So A times C is the matrix A. Okay, A is just A. Okay, so A times C, well, C is this. And in that case, you get A times this vector and this vector and this vector. Now that might take a little to work with. So I actually did this myself down here with a 2 by 2. I don't know if you can read all that very well, but just do like a little 2 by 2 and see if you can break it up to see that it's actually those vectors. Like this is your A, this is your V, A and V. And I don't, yeah, no, I guess that's basically it. Yeah, so you can see that you get that matrix. If you add those together, then that's what you're going to get. You're going to get these column vectors like that. Okay, so so check that with a 2 by 2 to see how you get this form. So those are equal, right? Meaning you end up getting AV equals lambda 1 V1. So that is by definition an eigenvalue and a corresponding eigenvector. That's this form, so they match up. Okay, so that's all you got to do. You just got to convince yourself that this product is this and this product is this, and then you're just equating those columns. Once you do that, that is by definition eigenvalues and eigenvectors. Okay, moving on to more definitions of a diagonalizable matrix. An n by n matrix A is diagonalizable if there exists an invertible matrix C such that C inverse times A times C is equal to D, a diagonal matrix. What we say then is C is said to diagonalize A. That's the concept. So a couple things to remind us of. So C is invertible for a number of reasons, but we're going to say if and only if the rank of C is equal to n, right? And C is an n by n matrix, which is the column vectors of C form a basis for n space. Okay, and if C exists, well, first of all, we have that the previous theorem, we know that A times C is equal to C times D as defined above. So then if C inverse exists, multiply both sides by C inverse. So you get C inverse AC equal to C inverse C times D. And then what is C inverse times C? Yeah, that's basically I. So you get C inverse A C is equal to D. Right, so and D is that diagonal matrix. So if you can basically decompose a matrix in this form and get D, so basically if you can do this, then the matrix D is much easier to work with. And you can operate on D instead of just A itself. So there's a lot of advantages to that. So let's go on to the corollaries. Corollary 1, let's see where we're at here. So this is corollary 1. Says an n by n diagonalizable matrix is diagonalizable if and only if n space has a basis consisting of eigenvectors of A. All right, so A n by n is called diagonalizable if and only if n space has a basis consisting of eigenvectors of A. Okay. So let's see. So corollary 2. This is all on page 307. Let's go to corollary 2. So corollary 2 basically says, all right, so those are quite a few things. So basically what we can write then, so given all the different hypotheses above, you can write A. I'm going to skip a bunch of this because it gets too long. So A to the K can be written as C times D C inverse. And you have that many factors, C times D C inverse. Kind of showing you how this works anyway. And so you have K factors of that. And then all C inverse C's are equal to I. So this ends up being just D to the K. Right, so you can end up, actually not just that, sorry. Just bring that back. So not just that. You end up getting C D to the K C inverse. I forgot the outsides are going to stay. This one and this one, all the ones in the middle. Basically, when these are adjacent, they're going to give you I, so you get all of that. So you can write, that's the corollary. So you can write A to the K like that. And so the D to the K is much easier to work with and calculate and has its benefits over just A. Okay, so a couple of those terms. We're going to look at, let's see, 1 or 2 more theorems. And then, yeah, well, there's a few things to do. So we'll see how we're doing. Let's move on to the next theorem, 5.3.